Alright, it's 9.7 today. This lesson is geared towards you learning two additional tests to determine if a series converges or diverges. So, first up, the direct comparison test, and then afterwards, the limit comparison test. So, these are comparisons, and so yeah, you're going to compare it to something. Now, with the direct comparison test, their goal is you've got a whole bunch of terms in a series, which we call A sub n. Okay? And there is another one called B sub n, and it's going to be bigger or equal to A sub n. Okay? So here's the deal. If the B sub n series converges, then the sum of the A sub n's must converge. So remember, this one's the bigger one, right? Bigger. So the bigger converges, or the larger, then the smaller also converges. And I hope you can visualize that, right? These are terms, and if they're all positive, they're all bigger, right? And that converges, then the series A sub n, which is always less than or equal to it, well, that must also converge. Okay? Similarly here, in number 2, if the smaller one diverges, okay, so all the summation of A sub n, all those terms go to infinity, then goes really large. Then, of course, if b is bigger than it, or larger, it must also diverge. So you can memorize that, or I'd really prefer this informal idea. The larger series converges, then the small series must converge. That's what this says. And if the smaller series diverges, then the larger one must also diverge. Okay? Remember that we have this thing here where all the terms have to be bigger than 0. So yes, the series must have positive terms. All right? So with that in mind, let's take a look at examples 1, 2, and 3. Here we've got 1, and this is pretty hard to figure out right away because it's 1 over 1 plus 2 to the power n. But if we can compare it to something very similar to that we can figure out if it's converging or diverging quite easily, then that makes our life a lot better. And what do you think we can compare this to? That's very simple. Yeah, you might be thinking that 1 in the denominator is really what's making life miserable for me. So you might be thinking, let's compare it to 1 over 2 to the power n. Well, sure, you can do that. And you can think about, what type of series this is. If you're not too sure, you can always write it out. So for example, if I plug in n equals 1, that's just like 1/2. And then what? 2 squared is 1/4. Then 1/8, and so on. Hopefully you'll see that there is a common ratio here. Therefore, this is a geometric series. Common ratio of r equals to 1/2. And we know that if the absolute value of r is less than 1, then we know this series converges, right, by the geometric series test. Great. So we figured out this converges. Now the question is this the larger series or the smaller one? So once again, we're trying to compare this with that. Okay. Now notice the one in blue, the denominator is bigger. Next I'm adding 1 to it compared to the green. So if the denominator is bigger, 1 over a bigger denominator is actually a smaller number. So I hope you can understand that. Yes, the expression 1 plus 2 to the n must be smaller than 1 over 2 to the n. And we know that all of these are bigger than 0. They're all positive since n has to be 1, 2, 3, or 5, or whatever. So knowing this, I can say by the direct comparison test. And the short form here is DCT. We know that the sum of n equals 1 to infinity of 1 over 1 plus 2 to the n, yes, also converges. Okay, so once again, we compared it to a different series that was a little bit easier to manage. We figured out if that one was converging or diverging. We then looked at which of the series were smaller and bigger to see if it fits in the actual definition from above in the direct comparison test, and then we come up with our conclusion. All right? So let's try number 2. N minus 2. Oh, what's an easier one? Yeah, I'd compare it with just 1 over n. Yep, so n equals to 3, infinity, 1 over n. Okay, we know 1 over n is like 1 over 3 plus 1 over 4 plus 1 over 5. This is a p series, or actually this is the harmonic series. So I'll say this is the harmonic series. Or you could say the p series with p equal to 1. And we know that that diverges. Okay, so this diverges. Okay, now, if this diverges, our goal hopefully is that this is the smaller one. We're going to use this. Number 2 here. Let's see if this is the smaller one. So, n versus n minus 2. N minus 2 is probably the smaller. 1 divided by smaller is bigger. So therefore, I think we can say that 1 over n minus 2 is bigger than 1 over n. And once again, all of these are all bigger than 0. So by the direct comparison test, we know that the sum of n equals to 3 to infinity of 1 over n minus 2 must be, that's right, diverges as well. Okay, there you go. Okay, number 3. That plus 1. Yeah, you're thinking, let's compare it to 1 over root n? Sure. I forgot my summation symbol. Oops. Compare to n equals to 1 infinity 1 over root n. And this must be a p series with a half, so that's less than 1. So therefore, this one diverges by the p series test, right? So if this diverges, then hopefully that's the smaller one, and then that shows that this one also diverges. But wait, which one is the actual smaller one when I compare these two? Root n versus root n plus 1. Well, the n plus 1 over here, oops, I should try a different color. N plus 1, of course, is bigger than root n. 1 over a bigger number is a smaller number, right? So what we have here is 1 over root n plus 1 is smaller than 1 over root n. But wait, we just said that the bigger one diverges. But up here, I need the smaller one to diverge. Uh-oh. That doesn't work. Uh-oh. Uh-oh. We did all that work for nothing. Doesn't work. Uh-oh. Uh-oh. So I'd like you to think about, is there another simple series I can compare this to? Hmm. I don't know. Well, maybe writing some terms might help. Let's see. Plugging in 1, that's 1 over 2. The next term of that will be 1 over root 2 plus 1. 1 over root 3 plus 1 plus 1 over root 4 plus 1. Okay, I know what that is. That's 2 plus 1, that's 3. I'm just curious if you're wondering what those numbers are. This is, of course, 0.5, and this is 0.414. This is 0.366, and of course you know this one, and so on. What can this be compared to? Hmm. Hmm. Perhaps if I were to compare it with something like this. the sum of n equals 1 to infinity of maybe 1 over n? Yeah? Would that be okay? What will that be? Okay, that will be like terms, well, 1, so that'll be 1 plus what? Half plus a third plus a fourth and so on. Yeah, we know, once again, this is a p series with p equals to 1, so therefore this diverges. Okay, so that's the same as before. But what's different about this one here? Which is bigger, root n plus 1 or, what did I say? Yeah, or 1 over n. That's right. Which one's bigger? So now I'm going to ask you to compare once again. Which one is bigger? This one in blue, 1 over root n plus 1, or 1 over root n? I hope you can reason that 1 over root n plus 1 is actually bigger than 1 over root n. Which is great, because if that is bigger, is it bigger, you're thinking? Wait a minute, you're like, wait a minute, it's not bigger, is it? Well, let's think. Let me compare 0.5 to 1 not bigger. Yeah, 0.4 1/2 not bigger. 0.336 not bigger. 0.333 1/4 not bigger. Oh wait. Oh wait. Okay. Not bigger. Yeah. Not bigger. Wait. Bigger. Wait. Bigger. Wait. Bigger. The rest of them are actually bigger. So this is true. This is actually true when the n value is bigger or equal to 3. So if you look at a series going further and further out, actually the terms of 1 over root n plus 1 is actually bigger than 1 over n. And yes, we know all these are bigger than 0. So because of that, now once again, not all the terms are bigger, right? The first two are not, but that's okay. That's only the first two terms. The rest are bigger. We then know by the direct comparison test the sum of n equals 1 to infinity of 1 over root n plus 1 does definitely diverge as well. Okay? So tricky. First of all, you gotta find the right series to compare it to. And then you might need to look a little bit deeper into the actual terms to see which one is actually bigger than the other. Okay. Now, if you couldn't see that right away, what you could have also done is if this was a question on the graphing calculator allowed portion of the test, you could have just graphed out these two functions and see when it's actually bigger. And what you would have found is that when n is bigger than or equal to 3, then of course the 1 over root n plus 1 term is actually bigger than 1 over n. Okay? All right. That's direct comparison. Oh, here's the next one called limit comparison. So a little bit similar because we're comparing things, but in this case, also a little bit different. Once again, we need to know that the terms of a sub n are all positive, and similarly, the other one we're comparing to is also positive. This one says that if you were to take the limit of the a sub n divided by the b sub n, as n goes to infinity, if this gives you a number L, which is finite, so it's a number, and positive, then what we know is that both a sub n and b sub n either both converge or they both diverge. Okay, so they follow the same pattern, right? One converges, the other one converges. One doesn't, the other one doesn't. So therefore, Not only that, you need to know that one of these things you're comparing to, you can quickly say that it converges or diverges. So that's why the limit comparison test actually works well when you're comparing a messy algebraic series to an easier p-series. Because once again, we know that the p-series, very easy, right? Less than or equal to 1, diverges. Bigger than 1, converges. So that helps us already identify one of the series, which either converges or diverges. That will help us now with the limit comparison test to figure out the other series if that converges or diverges. Okay, so let's take a look at how we can do that. So for example, number 4, I'm just curious here. What lovely, easier series can we compare this to? Yeah, you're thinking compare to, I know what you're thinking, because I'm thinking the same thing. 1 over n squared. Good. Once again, the p-value here equals to 2. That's bigger than 1, so by the p-series test, we know this converges. Yep. Okay. So now we know one of them converges. We can use this limit comparison. So let me set up my limit. The limit as n approaches to infinity. It's the a sub n. So I'll just take that as my original one, divided by my b sub n, which is my comparison one. And now I'm going to have to simplify this. This actually just becomes the limit of n approach to infinity of 1 over 3n squared minus 4 times the reciprocal. And then now how do we evaluate this limit? Remember, we can just use the n behavior model, which means just take n squared over 3n squared. That just actually simplifies to 1/3. 1/3 looks to be finite and positive. So what does that mean? By the limit comparison test. Can you guess what the abbreviation is for this one? Got it, LCT. What do we know? The sum of n equals 2 to infinity of 1 over 3n squared minus 4 converges, right? Because it follows the 1 over n squared term. Okay? All right. You got the idea? Let's see if you can figure out number 5 and also number 6. I think you can do this yourself, but if you're not too sure, I'll walk through it with you. If you are sure, try it yourself first. Okay? This is root n over n. That really simplifies to 1 over root n. So I'm really going to compare this to 1 over root n as my p-series. We know that the p-value here equals to a half. That's less than 1. So by the p-series test, the PST, we know this diverges. That's right. Now we can set up that limit fluff. Let's quickly do the limit comparison. That'll be root n over n plus 7. And by the way, instead of dividing by the 1 over root n, can I just quickly rewrite this as multiply by, what would that be? Yeah, root n over 1. This makes life a little bit easier. We know that this just then becomes the limit as n approaches to infinity of n over n plus 7, which if I take the n behavior is just n over n, which equals to 1. Once again, finite and positive. So therefore, by the limit comparison test, what do we know? That original summation also must diverge. Did you get that? If you did, give yourself a pat on the back. Bravo. Okay, last but not least, numero 6. Number 6. You're thinking, what comparison test can I compare this to? N over n cubed. Yeah, that simplifies to 1 over n squared. So definitely compare this to n equals 1 to infinity of 1 over n squared. We know that this is a p-series that's equal to 2, that's greater than 1, therefore by the p-series test, this converges. And now we'll do that limit n approach to infinity, n over 4n cubed plus n squared plus 5. Remember, we're dividing by 1 over n squared, so I'm going to multiply by n squared over 1. That simplifies to n cubed on the top, 4n cubed plus n squared plus 5 on the bottom. And then by the n behavior model, we're just going to look at the highest powers. And that simplifies to 1/4. I like that. Finite, positive. So therefore, by the limit comparison test, we know that the sum of n equals 1 to infinity of n over 4n cubed plus n squared plus 5 must also converge. Yeah. Bravo, if you got both of these on your own, you're now an expert at the limit comparison test. Okay. So just to let you know, there is one more test I need to talk to you about, and that's coming up in our next lesson. But once again, we are trying to find different ways of determining whether something converges or diverges. All right? And now you have 2 more tools in your toolbox: the direct comparison test and the limit comparison test. Do some questions now.